Hi everyone, my name is Thomas Kim. Today is September 28th, 2020. This is my 65th episode about vector calculus and classical electromagnetism. In this episode, I will discuss numerical integration using Gaussian Quadrature. The mathematical theory behind Gaussian Quadrature is quite complex. For example, we have to start with the Legendre polynomials from this Wikipedia. In this episode, I will not discuss Legendre polynomials, but in near future, I will explain how to generate Legendre polynomials and how to solve these Legendre polynomials numerically. But in this episode, I will not discuss Legendre polynomials. For Gaussian Quadrature, please double-click this link. We will refer to this Wikipedia in this episode, especially about this part. Also, change of intervals. We also need Gaussian Quadrature, weight and abscissae from this website. We will use weights and abscissae. How do I pronounce this word? We will use these tables. For general idea about Gaussian Quadrature, I found this video, Introduction to Numerical Integration through Gaussian Quadrature by Mr. Ben Lambert. He explains very well. He gives general idea behind Gaussian Quadrature. I would also recommend this video by Eric Davis Shaw. By watching this video and this video, you can get the big picture of Gaussian Quadrature. I will concern C++ implementation of Gaussian Quadrature. If you watch these two videos, then you can understand my session. In future episode, I will explain mathematical theory behind Legendre polynomial and Gaussian Quadrature. But in this episode, I will concentrate on C++ implementation. Please scroll down. In the download source code section, please double-click this link. This is source code from our previous episode. Right-click, unzip it, right-click, rename 065 Gaussian Quadrature. Copy, paste it to your working folder. Start Visual Studio Code. Open your working folder. Double-click this file. Select this folder. We will create Gaussian.cpp. Hit enter. Ctrl B. I will arrange like this. Include talk play fun, output HPP, include talk play fun, vector HPP, talk play fun, S stream, oro, NL, talk play fun, NL. Void test Gaussian Quadrature. int main, copy the function name, copy, paste it. Here, oro f is our function, oro x, return std sin x. This is the integrand that we will integrate from 0 to pi over 4 or 90 degrees. Here, scroll down right before end of namespace talk play fun, template, type name, value type, type name, function type, return type is value type, Gaussian Quadrature, value type, x1, value type, x2, function type, forwarding reference f int n 5, value type I, initialize to 0, return I. Here auto I equal talk play fun. We are calling this function 0 math m pi for f. F is defined here. I will call like this. String I equal I and L. Now let's try to build it. Start command prompt. dir cd 065 Gaussian Quadrature CLEHSC SCD C++17 Gaussian .cpp fe m.exe. Hit enter. Sorry, delete this. Let's rebuild. Okay, we built. So I scroll down, integrate function f. This function from x1 lower bound to x2 upper bound using Gaussian Quadrature with n. N is defined here. Wait, I need to explain some basics about Gaussian Quadrature. We want to integrate from x1, x2, fx, dx, minus 1, 1, gt, dt. We have to convert x1 to minus 1, x2 to 1, x to t, dx to dt. To do that, we let x equals at plus b. If we differentiate dx over dt equals a, so dx equals a dt. We need this equation. This is equation 1. This is equation 2. And we have to find a, b. When x is 1, t is minus 1. X is 2, t is 1. We substitute x1 minus 1 into this equation 1. x1 equals a minus 1 plus b. We substitute this point x2 1 into equation 1. x2 equals a 1 plus b. We subtract term by term. x1 minus x2 equals, this is minus, so minus 2a. Because we subtract, b cancels out. From this result, we have a equals x2 minus x1 over 2. We need this result. I will call it 3. If we substitute a into this equation, x1 equals, in place of a, x2 minus x1 over 2 minus 1 plus b. If we arrange this equation, b equals x2 plus x1 over 2. We need this result. This result is 4. If we substitute equation 1 to this equation, fx equal f, we substitute at plus b, 4x at plus b. This is gt. We need this result. This result is 5. Integral x1, x2, fx dx equals minus 1, 1. For gt, we substitute f of at plus b. f at plus b. For dx, we substitute a dt. Then we have, because a is constant, a 1 minus 1 f at plus b dt. Gaussian quadrature says that minus 1 f at plus b dt can be approximated w1 f at1 plus b plus w2 f at2 plus b plus w3 f at3 plus b plus w4 f at4 plus b plus w5 f at5 plus b. Gaussian quadrature says that there are w1, t1, w2, t2, wn, tn. These numbers, using Gaussian quadrature, we can compute this value using this equation with these magic numbers. I will call these magic numbers. So these magic numbers are listed here. In this table, when n is 2, wi, this is w1, this is t1, this is w2, this is t2. When n is 5, this is w1, this is t1, this is w5, this is t5. So wi, xi, using these magic numbers, we can evaluate this integral. Then we can approximate this integration. Now we have to implement a function that returns w1, t1, w2, t2. I will arrange like this. I will close it for the time being. Here, template, type name, value type, or I will call this function weights Abscissae int n5 using var t std var value type using weight Abscissae t std vector. We provide var t. I will change wat. Switch n from this table case 2, return wat weight Abscissae weight Abscissae I will arrange it like this. Case 3, return WAT, weight, Abscissae, weight, Abscissae, weight, Abscissae. We will return WP T to prevent warning. So we implemented weight Abscissae. Now here auto weight Abscissae, we call this function. We have to provide element type. Then we pass n. I will arrange side by side like this. We first need to compute equation 3a auto a equals x2 minus x1 over 2 auto b x2 plus x1 x2 plus x1 over 2. We now call this part is loop. For auto R value reference, W is weight T. We use WA. Sorry, I have to paste it here. We call function f. Please note that A times T comes from here, plus B. We are calling this part FAT plus B. We multiply W and sum up like this. So we summed up all these terms. This part evaluates this part. So I times A, because we have to multiply A. This part sums up this part and evaluates this part. So we have to multiply A here. Now we can return. Just so you know, integral 0 pi over 2 sine x dx, the exact value is 2 minus square root 2. This is the exact value. I will arrange once again. Now open Gaussian.cpp, Ctrl B. In the Gaussian.cpp, we integrate sine function from 0 to m54. Sorry, this is wrong. This is pi over 4. Then auto see the correct value is 2.0 minus SED square root 2.0 over 2.0. C is I is approximation. C is the correct. Auto error STD FAVS correct value minus approximation string error. In the command prompt, we fill again 343. I expand it. This is WA. I have to fix. Now I will maximize it. In the Gaussian.cpp again, I made a mistake here. Also, stream, std, precision 19. Now in the command prompt again, we build CLSM. So our approximation is correct up to 14 decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14. 14 decimal places. Here we give 7. We build again CLSM. Our Gaussian Quadrature approximation matches exactly with the result of algebraic computation. Error is 0. Gaussian Quadrature is a super powerful numerical integration algorithm. This is one of the most important and well-known numerical integration algorithms.